going to introduce contingency tables, looking at two variables at the same time for individuals in a sort of made-up sample, an illustration that we're going to use to introduce an idea called chi-square. Let's start with just the idea we have two variables. One is vote and one is gender. We'll call vote V, gender G, and let's say we have a simple random sample of 100. N is going to equal 100, and on gender, we'll put it here. It's categorical, maybe nominal, maybe absolute measures. I'm going to address that in the next video. Female, male. These are exhaustive categories in this sample. And here we'll go Obama versus Romney. So I have an N of 100, and I'm going to spread these out. So I'm going to have 50 observations in each margin. And for the subsequent videos and working with chi-square in general, a test of the association, or test of non-independence, as it turns out, of these two variables. I'm going to need to know the terminology. So these are row marginals. These are actually column marginals. These then are row marginals. And I'm going to make a gender gap, which we'll test with chi-square in the next video. I'll make a gender gap. Say that 30 of my females. So I'm going to make this smaller. So I'm going to put 30 females were for Obama. 20 of the 50 were for Romney, and the exact opposite occurred among males. This is all hypothetical. There was a gender gap, of course, in 2012. But these are made up data. 20 have the mirror result where only 20 of the 50 males are for Obama, 30 are for Romney. These are raw counts. These are cell entries in a contingency table. These are again the column marginals. Those are the row marginals. For presentation purposes, I often like to look at percentages in these tables, and if you're sort of making it to visualize data for someone else, it's important to do that. There are three different types of percentages that can belong in any of the three. I'm not going to illustrate them, I'm just going to explain them. So you could illustrate percentages by row, wondering what percent of 50 is 30, and list that here. What percent of 50 here is 30. You could do it by column, happenstance, you have the same number. Or you could do it by cell. So the percentage in each cell of the total, row, column, or overall. It's by definition set up here. Overall is what appears here, even with the raw counts, because 30 is 30% of 100, and likewise 20%. But to set this up for visualization, you would want to use percentages either by row, by column, or overall. What else do we want to see here? That's it. We're going to have two more little things to show before we go to the chi-square problem. One, so that you can get in your notes very big, the definition of chi-square. In the previous, before I erase the board with the nifty thing, We had a 2x2 table, one that's in a subsequent video. We'll take our first cut at calculating chi-square momentarily. First, I want to define it for you. This scares some people. This is adding, subtracting, and multiplying and dividing, and nothing more than that. Chi-square is a family of distributions that differ in shape and in terms of the area underneath the curve based on the size of the table, right? So we call it degrees of freedom. We'll see that in a minute. Different ones have different degrees of freedom, but you calculate it simply by making a calculation inside each cell. So a minute ago, here's what I just erased. The observed frequency, which is what FO means. FO means observed frequency. I want to write that down. F sub E is the expected frequency. That difference is squared. Chi-square is a distribution of a sum of squares. We're going to add those up. This thing then divided by FE. Show you how to do that in a moment, or in the subsequent video. Observed here is 30. Observed here is 20. You do this calculation in every cell, and then once you've done it in every cell, by hand, or you're just going to do it with a computer, obviously. Once you've done it by hand in every cell, you simply add up these calculations inside each cell. I'm going to have a little table in the next video, too, that I want to show you very briefly. It's sort of the finish. It's got degrees of freedom. Seen that kind of 4.05, the sort of traditional rule of thumb way to say something is statistically significant that we are going to avoid doing ourselves and yet recognize as part of normal social science. I'm going to have degrees of freedom this way, 2.71, 0.84, and 6.63. I have a more full version of this table. It's just a reference inside the table of values of chi-square that are associated with p-values. Yes, p-values are back and are used in sort of judging the confidence that we have in making an assertion that two variables are or are not related. Another way to state that more formally here is to say that these two variables are not independent. A very strong assumption, harkening back to discussion of probability. So if we got a chi-square value, we have 1 degree of freedom, which it turns out we will for the next example. If we have 1 degree of freedom, we got a chi-square value larger than 4.0, we would pass the magic value, 0.05, and say that it's a statistically significant result if we were that kind of person. And likewise, we'd say it's a 99% confidence if we got a chi-square of 6.63. These things are going to appear on the next video shrunken. So you're going to get, depending on the quality of your playback, you'll be able to see them in highest quality, but not necessarily as well as you might want. So these notes are important for understanding the next video. That's all for now.